So for this part, we will show that modifying a function on the set of measure 0 does not affect the value of the Lebesgue integral. But before that, we define what do we mean by the phrase almost everywhere. So a certain property is said to hold mu almost everywhere with respect to a certain measure mu, and it will be abbreviated by mu AE. So if that property or the set for which the property fails has measure 0. So for instance, if I have two measurable functions, f and g, then we say that f is equal to g, mu almost everywhere, if and only if the measure of the set of points in X where f is not equal to g is 0. And from this, if either, okay, the functions are non-negative, or they are Lebesgue integrable, then and they are equal almost everywhere, then the Lebesgue integral coincide. The Lebesgue integrals are the same. And to show this, it is enough to show that, okay? So as the first step, if f is less than or equal to g, mu almost everywhere, then the Lebesgue integral of f d mu is less than or equal to the Lebesgue integral of g d mu. Now, if this is the case, take note that if f is equal to g, mu almost everywhere, then the set of points, let's say where f is greater than g, this is of course non-negative. This is the set where f is equal to g is a subset where f is not equal to g, because it is possible that g is less than f, but by assumption this is 0. So this implies that the function f is less than g mu almost everywhere. And similarly, if you look at the set of points where f is less than g, again, that set is a subset of the set of points where f is not equal to g. And we see that f is, or g is less than or equal to f mu almost everywhere. So from the first inequality, we get this one. And on the second property, we get the reverse inequality. So this is 2. And hence, the two integrals must be the same. So step 2 implies the desired equality of Lebesgue integrals as long as step 1 is valid. So now let us prove step 1. And for this, it is, let's say, or we consider two cases, of course. First, let us suppose that the two functions are non-negative and measurable, and f is less than g mu almost everywhere. Let us define, for simplicity, the set n, where f is greater than g. Then, by assumption of f being less than or equal to g mu almost everywhere, therefore the measure of n is 0. And in fact, one can show that f times the indicator function of the complement of n is less than or equal to g. So if the point is in the complement, then the reverse inequality here must be satisfied. So that is f is less than or equal to g. On the other hand, if f is in the complement of n, or not in the complement of n, so this is 0, and you use the fact that g is non-negative. So in any case, this inequality is satisfied. So starting from the Lebesgue integral of f as a non-negative function, we split this into two parts. One, by multiplying the indicator function of the null set n and the indicator function of the complement. Okay, so take note that this is equal to 0 mu almost everywhere. And since this is 0, except on a null set, the Lebesgue integral must be 0. And we end up with the following integral of the second term. You apply monotonicity, and this is less than or equal to the Lebesgue integral of g. So that's the case of non-negative measurable functions. Now, I'll suppose that f and g are Lebesgue integrable. They are real valued. And again, f is less than or equal to g mu almost everywhere. Then one can see that g is less than or f plus is less than or equal to g plus mu almost everywhere, and the negative part of g is less than or equal to the negative part of f mu almost everywhere. Again, using this, starting from the Lebesgue integral of f, by the definition, this is the difference of the Lebesgue integrals for the positive and negative parts. Now, applying the m plus case, since f plus is less than or equal to g plus mu almost everywhere, then this integral holds. And for f minus, after multiplying by a -1, then you obtain this second term. However, this is nothing but the Lebesgue integral of G. Okay, so that's the case of uh, the real valued functions. Okay, so that's the proof of the in this case the theorem. Okay. So again, if two functions are equal except on a set of measure 0, or in other words, they're equal almost everywhere, then the Lebesgue integrals coincide. And this follows from this crucial part of step 1, that if f is less than or equal to g, mu almost everywhere, then the same inequality holds for the Lebesgue integrals. Now, let us prove some sort of a converse, okay, this is statement. So if I have two Lebesgue integrable functions and the inequality, the following inequality for the Lebesgue integral holds. Now for all measurable sets A, then we are guaranteed that f is less than g, mu almost everywhere. So if the integral over measurable sets satisfies this inequality, then the integrand must be true in this case. Well, to look at the proof of this statement, again, let us denote by n the set where the inequality is violated. And we will show that the measure of n must be 0. Again, we approximate this by n sub n. So this is the set of where f is greater than g plus 1 over n. Then this sequence n sub n is increasing, and it increases to capital N. So here, starting from the Lebesgue integral of f, we apply, let's say, the set is n sub n. We apply monotonicity. So this is the integral of g plus 1 over n. So here, that's the reason why we restricted the integral over n to the n, because we know this property here. And this is equal to, by the linearity of the Lebesgue integral, mu of n sub n. And the assumption, okay, this is assumption here. If I take n, or I should say a to be n sub n, and of course, this is in sigma due to the measurability of f and g. So this is greater than the integral of f d mu plus 1 over n mu of n. Okay, so this 2 will cancel. So the measure of n sub n must be 0, since the measure is always non-negative. So again, applying the continuity of your measure and the fact that n sub n increases to capital N, the measure of the set n is 0. That is, f must be less than g, u almost everywhere. Okay, so we have, as I said, some sort of a partial converse of the previous statement. So if the integrals satisfy this inequality for every measurable set A, then the integrands must satisfy the same inequality. So to close this chapter on Lebesgue integration, let us now discuss the other convergence theorems for this new integral that we have considered. So let us recall the monotone convergence theorem last time. So for the monotone convergence theorem, if you have an increasing sequence of non-negative measurable functions, then you can interchange the limits at the integration. Now, what if we want to relax that statement? In other words, what if we ignore the assumption that the sequence is increasing? So our assumption is now weaker, so we expect that the conclusion is also weaker. And indeed, we have the so-called Fatos lemma. So let's start with a sequence with measurable functions that are non-negative. Well, we know that the Lebesgue integral is unchanged for a set of measure 0, so we can assume that the sequence is non-negative almost everywhere. And then the integral of the limit inferior of the sequence is less than or equal to the limit inferior of the integrals. So take note here, we remove the assumption that the sequence is increasing. So we have a weaker assumption, therefore it is natural that the conclusion is also weaker. So instead of the limit, we have the limit inferior, and instead of equality, we have an inequality. Okay, according to the previous discussion, since the Lebesgue integral is not affected if we change the function on a set of measure 0, so by redefining the sequence of functions to be 0, where it is negative, we can assume without loss of generality that the sequence is non-negative for all n. Okay. And in this case, let us introduce a new sequence of functions, say g sub n, and define this to be the infimum of f sub k, where k is greater than or equal to n. Each f sub k are measurable, therefore the infimum is also measurable. And since we assume that the sequence of functions are now non-negative, this g sub n is also non-negative. Then we have, so gn being the infimum, this must be less than or equal to a specific function in the sequence. And here we take the smallest, namely n. The sequence is increasing since if you increase the index, you consider a smaller collection of functions. And Gn tends to the limit inferior of f sub n as n goes to infinity. Okay, so to modify the index to avoid confusion, let us denote the index for G by M. Okay, this G sub M, G sub M. So as M goes to infinity. So to prove the inequality, let's start with the left-hand side. So that's the integral of the limit inferior. So our goal is to put this limit inferior outside. By definition, the limit inferior, this is the same as the limit or the integrand, the integral of the limit as m goes to infinity of G sub m. And in this case, since Gm increases to the limit inferior, this implies that, okay, applying the monotone convergence theorem, so we can pull out the limit since the sequence is now increasing. And since the limit exists, it is the same as the limit inferior. Now re-indexing, we'll have G sub n here. And we know that G sub m or G sub n is less than f sub n by applying monotonicity. This is less than or equal to the limit inferior of the integral of f sub n. And this is the desired inequality. Okay, so here, in fact, we can have a strict inequality, and it is provided in the following example. So we can have a strict inequality in Fato's lemma. Well, let us consider the function, the real valued function f sub n under the n-dimensional Lebesgue measure. So this is the characteristic function of the closed interval negative 1 over 2 to the n, 1 over 2 to the n. So here the height is n and the base is located in this interval. So this is clearly, of course, non-negative and measurable, being the characteristic function or being a simple function. Okay, so computing the Lebesgue integral with respect to the Lebesgue measure, being a simple function, this is n times, okay, but the Lebesgue measure of this closed interval is 1 over n, so therefore this is 1. On the other hand, note that if we, or we can say that Fn tends to 0, mu almost everywhere, or lambda almost everywhere, since this is true except on the point where x is 0. So the integral, the limit inferior, which is in this case the same as the limit, is 0. Okay, so the left-hand side in Fato's lemma is 0, while the right-hand side is equal to 1. So here we have an example where a strict inequality holds for the Fato's lemma. A consequence of this is the following. So what if we instead having a bound 0, we have a bound that is also integrable. And the generalization is what we call the Lebesgue-Fatu lemma. So let us consider a sequence of measurable functions and an integrable function g. So first, if f sub n is bounded from below by the integrable function g, mu almost everywhere for all n, then the same conclusion for the Fatu's lemma holds. On the other hand, if f sub n is bounded from above by the integrable function g almost everywhere for any n, then instead of the limit inferior, we have the limit superior. And the inequality is now reversed. Okay, so the first one is a generalization of the Fatu's lemma, where you can take g to be the 0 function, which is obviously integrable, having integral 0. The second one is another version where instead of the limit inferior, you have the limit superior, but of course you need to reverse the inequality. Okay, so for the proof, the first one, we will reduce this in the case of the usual Fatu's lemma. So you take the difference both sides, or subtract g both sides, then you have fn minus g mu almost everywhere. And we note that the difference of two measurable functions is also measurable. We now apply Fato's lemma to this new sequence fn minus g. So limit inferior as n goes to infinity of f sub n minus g d mu. This is less or equal to the term when the limit inferior is pulled out. Okay, so the left-hand side, we can distribute the limit inferior and take note that the second term, g, is independent on the n. After applying linearity, we get this difference. And similarly, on the right-hand side, we get the following difference. So therefore, after adding the integral of g both sides, you end up with the same conclusion as with the Fato's lemma. Okay, so for the second case, if f sub n is less than g, then multiplying by a negative sign, negative f sub n is greater than negative g, mu almost everywhere. The negative of f sub n is measurable, and that negative g is also Lebesgue integrable. So now we apply the first case to the negative versions. So the integral of the limit inferior of negative f sub n is less than or equal to the limit inferior of the integral of negative f of n d mu. This one, okay, so pulling out the negative will give you the limit superior. And applying linearity of the Lebesgue integral, left-hand side is the negative of the limit superior. Doing the same manner, but in reverse order, that is, applying linearity and then pulling out the limit, the negative sign outside the limit inferior, you will get this term. And now you see why the inequality is reversed, because multiplying by -1, you will get this conclusion here. Okay, so that's the Lebesgue-Fatou lemma. Again, the first statement is a generalization of your Fatou's lemma, while the second statement is an analogous version where instead of the limit inferior, you have a limit superior. But now the functions, or the sequence of functions is bounded or majorized by a Lebesgue integrable function. Finally, we have the so-called Lebesgue-dominated convergence theorem. which was obtained by the French mathematician Henri Lebesgue. So for this statement, let us consider a measurable function. It can be complex valued or extended real valued. And let G be Lebesgue integrable. If, let's say, you have convergence for some f, you almost everywhere, and that your sequence is dominated by G in the sense that the magnitude of f sub n is less than or equal to G, you almost everywhere for all n, then f sub n and f are also Lebesgue integrable, and we can interchange the limit. So the integral of the limit of your sequence of functions is the same as the limit of integrals. So if you have convergence almost everywhere and your sequence is bounded by or dominated by some integrable function, then it is possible to interchange the processes of taking limits and integrals. So let us take up the proof of this celebrated theorem. G being integrable implies that f sub n and f are also integrable by monotonicity. Okay, so the first one, f sub n being integrable, follows from this inequality. The second one, well, f being the limit of, or being the pointwise limit of measurable functions is also measurable. And it is integrable since passing to n to infinity here, we note that the limit is also dominated by G, almost everywhere. So that's integrability of your sequence and f. Just merely applying monotonicity of the Lebesgue integral. Now we proceed with the proof of this equation here. And we only do this for the real case. Again, the complex case can be established by simply separating again the real and imaginary parts. Okay. We have note that according to the assumption, Fn is bounded from below by negative g and bounded from above by g, mu almost everywhere. And we know that plus or minus g is integrable. Okay, negative g is integrable, since we know that the space of Lebesgue integrable functions form a vector space. So let's start with the left-hand side. That's the integral of the limit the mu. Okay, so this is the same since the limit exists pointwise. The limit is the same as the limit inferior. Now, since f sub n is dominated by some integrable function g, we can apply here the Lebesgue-Fatou lemma, namely the first case. Okay. Or I should say the second or the first inequality. Okay. So f sub n is bounded from below by an integrable function. So the first version of the Lebesgue-Fatou lemma, namely the limit inferior version, we have this. However, the limit inferior is less than the limit superior. Now, we utilize, again, the Lebesgue-Fatou lemma for the case of the limit superior. So now you need that your function is less than or equal to some integrable function. But in this case, that statement or that inequality is valid for this integrable function g. So this is less than or equal to the integral of the limit superior. So let us check again. So if we want to pull inside the limit superior, we will have a larger value. Possibly a larger value. Okay, so we know that the limit of f sub n exists pointwise. So the limit superior is also the limit inferior. Okay, so we end up with what we started. In other words, we have these two same terms here. Therefore, all terms are equal by transitivity. So in particular, if that is the case, then these two are equal. And in turn, both of them are equal to the limit of the integrals. So the limit inferior is the same as the limit superior, therefore the limit coincides with the common value. And highlighting, so if all of these terms are equal, if we highlight this and this is precisely our goal in this theorem. So the proof of the Lebesgue-dominated convergence theorem follows directly from the Lebesgue-Fatou lemma. So Going back to our previous discussions, so first we started with the monotone convergence theorem. We applied this to prove the Fatus lemma, and generalize this, of course, in the case of the limit superior for and the limit inferior. Instead of having a lower bound 0, we have a lower bound that is an integrable function, and that is the Lebesgue-Fatou lemma. And this can be utilized in the proof of the Lebesgue-dominated convergence theorem. So those are the transitions in establishing these well-known convergence theorems for the Lebesgue integral. So this dominated convergence theorem is very useful, and it can can be used to prove other properties. For instance, interchanging integrals and summation, or infinite series to be precise. Even interchanging derivatives and integrals under suitable conditions of your integrand. And that is the Leibniz theorem. And later in the succeeding series of lectures, we will also use this to establish the interchangeability of the order of integration, namely the Fubini-Tonelli theorem, and as well as the formula for the change of variables with respect to integration. And that's it for now in the chapter of the Lebesgue integral. In the succeeding lectures, we will discuss further measure theory and further integration theory. So see you then.